that. Good morning, everybody. How are you doing? How is break? How does it feel to be in the building? What? Not good? You hate it. It's terrible. The weather is awful. We had to go outside once. Oh, yeah. No, it's great. We'll have great fun in here, okay? I've got things lined up. I specifically looked into, okay, how can I make sure there's always something fun to do each week, okay? We're going to have a great time in here. And those poor saps that are stuck at home online are just going to have to deal with the, less fun version. All right, we are in the middle of a area section, okay? Section 3.2 was more area formulas. Okay? No new major concepts to deal with, but more formulas. Hey, what about other shapes? Because we started with rectangles, or I guess, yeah, rectangles and triangles. Right? We said, well, there's more to life than just rectangles and triangles. Okay? What do we do with the other things? So that's what we figured out in this section. And so we've got a fair variety of problems. Today's problem set, fairly basic types of exercises. Okay? We've just got some practice there. You've got to get those basics down so that it's not obnoxious. So that when you do get to the much more interesting problems like in 29, okay, dealing with delicious, delicious pizza, how to get the most pizza for your buck, okay? Real world application. You want to know this, don't you? Doesn't everybody, you want to save some money, get the most pizza possible, okay? Right? But we got to practice with the usual. So I've queued up for us a short set of examples. We'll go through these together. And then I will leave the rest to you guys to start on the problem set today. The quizzes I am saving. We're still going to have our weekly quizzes, but I'm moving that to Tuesdays. Because Tuesdays is going to be online days. Right? So we'll put the quizzes on online stuff. And that way, the in-person advantage for you guys is as maximized as possible. You get the most problem working time with me here to help. Okay? Any questions about that? We'll get started. Ready to dive in? Okay. First up, parallelograms. They're like rectangles, but tilted. Okay? If you want to find the area of a parallelogram, I'm going to multiply two numbers, right? We're always multiplying at least two numbers. I hope we can pick up on that pattern recognition, right? Area, two-dimensional surface, we need two things. And not just any two measurement. What must be true about those two measurements? Can we pick any two numbers from our parallelogram? Can we? Any two you like? Will they always give us the same answer? Will any two give us the correct answer? Or does it need to be a specific two? What's that? I still didn't hear you. Say it louder. Specific. Yeah. It's going to have to be specific. We can't just pick any two numbers. I mean, look at those numbers. We've got three different measurements here. I think we can already consider that if a different combination of two numbers would give me a different result, yes? There's only one correct answer. This is math class after all. So it's got to be specific. Now, which ones are we going to use? And how do you know? What would you like to start with? Pick one. I didn't post the video to the classroom page. Let me do that now. Any top candidates? Ashley, which numbers do you like best? Which ones scream to you? These are the area numbers. I just know it. Louder, please. The bottom one? And? What's the other one? 2 or 1.8? 2? You like 2? 2 is pretty good. So how would you represent, like, if I want those two numbers, then I'm saying I always want two sides, right? This guy, this orange line in the middle, is not one of the sides of the parallelogram. Agreed? Orange line, not one of the sides. So Ashley is proposing we always want to multiply two sides of the parallelogram. Sounds pretty good. It's an easy enough rule to remember. Not going to work, though, unfortunately. Imagine, if you will, I chop this parallelogram into pieces. Let me get a different color here, right? If I sliced down that orange line and I had a triangle now, what the? It's always going to... Triangle, there we go. Now which ones would I want to multiply? I'd want to multiply this side and that side, right? Now it looks like, hey, it's a base and a height of a triangle, right? Of a right triangle, you always have what kind of angle here? Right angle. You always multiply those perpendicular bases. That was that funny business when we saw those other triangles. How do you deal with an obtuse triangle, right? One that looks like, I always forget that I can't have two sides snap, right? Like that, you can't just multiply these two sides. You had to get that perpendicular height that was out there. Remember that? Same thing with the parallelograms. Every area comes from multiplying two perpendicular measurements. Your two measurements must always come from lines or segments that are perpendicular. They make a right angle. So Ashley, which ones do you like now? Which ones look perpendicular to you? So we're going to stick with the 2.5? No? Yes. And the 1.8, right? Because there's a right angle there. These guys make a right angle. This is a base of my parallelogram. Right? I didn't mark this one up, but I told you it's a parallelogram. So we can safely assume that the opposite sides are, in fact, congruent, like they're supposed to be. So it doesn't matter which base I use. But I have to have a perpendicular height. So it's base times height all over again. Same thing. Rectangle, base times height. Triangle, base times height, times a half. You throw that in there. But conceptually, still base times height. Parallelogram, base times height. Height is always measured perpendicularly. If it's not perpendicular to the ground, to the floor, to the base, it ain't a height. It's going to get extra tricky when we get to the three-dimensional surface area, but now, if it ain't perpendicular, it ain't a height, and you're not multiplying. Always multiply perpendicular. So, area of this parallelogram will be, let me make some space here, 1.8 times 2.5, which is how much? $4.5? Can I get a confirmation on that? Anyone second 4.5? I see a head nod, Julissa. You're saying yes, it's 4.5? Okay. And what are the units? These measurements were in meters, so the units of our area is meters square, right? Area is always going to be in square units. 4.5 meters squared. Any questions on area of a parallelogram? Okay. The easy stuff, the exercises, is here's a parallelogram, find its area. The hard bit comes in problem format, where they disguise it. They set something up. I'm fencing in my backyard, and I want to go, you know, behind the house, but behind this tree, and over to the side of this, and oh, there's, right? You're like, most backyards are usually square. Sometimes they can be odd trapezoids, parallelograms, right? What do you do then? Right? You try to disguise it. They stick it in there. But anytime you can uncover, draw a picture for the problem, and you come up with, oh, hey, it's a parallelogram. I know how to deal with parallelograms. And away you go. Okay, next up, trapezoid. Here's a trapezoid. How do we deal with this guy? Area of anything can be two perpendicular measurements. Typically, base times height is what we like to call them. So I've drawn in a right angle for you. So right now it looks really tempting. Immediately say, that 9 is perpendicular to the 23. The area of the trapezoid is 9 times 23. Sounds pretty good, right? Good place to start. But 9 times 23, that would give you the area of this whole rectangle, right? I don't have that whole rectangle. I've only got the trapezoid. Okay, but Mr. Apple, I know that trapezoids have two parallel bases, which means that this side is parallel to that side. So if this is perpendicular down here, it must also be perpendicular up there. Ah, you make an excellent point. So could we use the 15 as our base? 15 times 9 would be our area. 15 times 9 gives you that little rectangle in there. That's not big enough. Now, the blue one went overboard, and the purple one is underboard, right? One's too big, one's too small. If one's too big and one's too small, what's a good way to like find the middle ground? All right, guys, compromise. Okay, don't fight. We'll meet in the middle and find the what? It's a good word that starts with A. What's that? I mean, ultimately, we will find the area. But when you want to like compromise between two numbers, you compute the what? Starts with A. How to find a number between two numbers that starts with A? No? If I add them both up and then divide by how many, that's finding the what? Oh, average. Find the average. Okay, that's okay. It's not a geometry term, so I blame your past teachers. All right. Average of the bases, right? If we found the average of the two rectangles, right? This one's too big, one's too small. The average will be just right? We're going for that Goldilocks area. So it turns out the area for a trapezoid is to literally take the two bases, 15, in this case 23, add them up and divide by 2. The average of the bases, and then multiply by the height, in this case 9. Sometimes you'll see this as a 1/2 out in front. It'll say 1/2 times height times base 1 plus base 2. Okay? I don't like that format because you lose why these are being added and why that 1/2 is there. Okay? It's literally the average. One's too big, one's too small. We'll find the average of them. Get that middle rectangle will be an equivalent area. Average the bases, then multiply by height. Our average size rectangle will have the same area as our trapezoid. So run that calculation. 15 plus 23 is 38 divided by 2 is 19. 19 times 9. It's almost 20 times 9, so 180 minus 9, 171. Okay, what are the units? The measurements were in centimeters, so our area is in centimeters squared. Very good. Any questions on trapezoids? Oh, the actual thing, yeah. Trapezoids are the toughest one, of the quadrilaterals at least, right? But it's the most versatile. Because there's a lot of things when you get to like real life that are almost but not quite actually perfect rectangles or parallelograms, and it turns out it's actually a trapezoid. So you're better off approximating it with a trapezoid. Okay. Next up, we have the regular polygon. This one's cool. I love area of regular polygons because it always breaks down in a really cool way. Every polygon, as we saw with what we were doing, interior angles of polygons, we could always cut it into triangles, right? That's just a handy trick. We should almost add it to our problem-solving strategies. When in doubt, turn it into triangles, because we know everything about triangles. But in this case, we're going to draw our triangles from that center point, okay? And we're going to cut this up like a pie. And if that is the true center point, and this is a regular polygon, then all of those triangles will be exactly the same. They are congruent, which means they will all have the same area. Which means if I want to find the area of my, in this case, pentagon, I'm going to take 5 times the area of a triangle, right? Just find the triangle and multiply. I've got 5 of them there. Boom, times 5, right? If you got an octagon, turn it into, octagon is 8 sides, turn it into 8 triangles. Find the area of a triangle, multiply it times 8. Okay? So top level, big picture, regular polygon. Turn it into triangles, cut it up like a pie. Find one triangle area, multiply by how many you got. Simple enough, okay? How do we find the area of that triangle? Oops. Area of triangle. Area of a triangle is always, everybody, what comes first? Any area. What? Base times height. But for a triangle, I also do what? Divide by 2. Or you can multiply by 1/2, whichever you prefer. Okay, remember our bases and heights have to be perpendicular to each other. Don't just pick anything. My pentagon is regular, so this 18 is the same as this side is 18, and this is 18, and this is 18, and this is 18. Find that perpendicular. Ooh, there it is. There's my right angle. So I've got an 18 here, perpendicular to this line here says it's 15, right? So that's what we're going to multiply. That's our base and our height of our triangle. Remember we had a fancy term for this line? From the center, perpendicular to the side of a polygon. Anyone remember what that is from the notes? was the apothem. But when you turn it into a triangle, now it's just the height of a triangle. Oh, I know how to use that. So our area of the pentagon is 5 times base of the triangle is 18, height of the triangle is 15, divided by 2. I'm going to save myself a little bit of trouble. I see that 18 there is even, so let's just go ahead and do the divide by 2, 9. 5 times 9 times 15. Is how much? Or do 5 times 18 times 15 and divide by 2. I like trying to make numbers smaller first, whenever possible. So if I see something I can reduce quick and easy, I will do so. Then start typing, right? That's several fewer buttons that I have to press into my calculator if I resort to that. So what do I get? (675 inches squared). Anyone have a different number? Okay. Any questions on how to deal with a regular polygon? If you notice, we can kind of shorthand this, right? This is where that reduced formula from the book comes in. Right? That height is our apothem. That's A. Right? Times the base, and the base times our number of sides always gave us the perimeter. And we still had the divide by 2, right? That's where that comes from. So you have the apothem times the perimeter divided by 2. That can be a handy shortcut sometimes, if you want to use it. Not necessary if you want to just... I mentally just still break them into triangles. I don't try to memorize this apothem times perimeter thing. It's all triangles to me. Okay, we got one more. Are you ready? Circles. And area of one circle I thought was a little too simple, so let's change it up. Let's do the area of a donut without making me too hungry. This would be a gigantic donut. Let's call this a flotation device, right? It is an inner tube. It's still pretty freaking huge, actually. 10 feet radius. I don't know, large floating platform. Anyways, we want to find the area of the donut. So not just the circle, but just the area between the two circles. If ever you're finding the area between two things, you are going to need to use what operation? Any guesses? Subtraction, right? Okay, if you want to make a note to yourself, right? Area between is always area of the big minus area of the small. Or the outside minus the inside, whatever you want to call it, right? That's how you get the area between. So in this case, we have two circles. So our area is our final area will be the area of the large circle, the 10-foot circle, minus the area of the 3-foot circle. I'm just using subscripts to refer to them there. In general, area of any circle is What's the formula? Guys remember? Check your notes if you don't remember. Come on, it's one of math's most delicious formulas. Pi r square. No, they're not. Pi are round. Joe, ever baked a square pie? Depends on what pan you have. All right, pi r squared, right? Pi times the radius squared. Area of our circle. That's not bad. So, area of the 10-foot circle is going to be pi times 10 squared, right? It's just the 10 that gets squared, not the pi. And then we have to subtract the area of the 3-foot circle. Pi times 3 squared. Try to get into the habit of writing this out as one big equation. It looks scary, it looks a little bit intimidating. Like, I'd rather just calculate the big one, calculate the small one, and subtract them at the end. I know you would. That's the easy way out, okay? That's how the elementary kids do it. We can do better, right? We're in high school now. We're going to tackle big equations. Because when you tackle the big equation, you can see other things that, hey, maybe I can simplify this and make my computation A, easier, B, more accurate, or both, right? So the thing I'm noticing here is that both terms, okay, these are two terms. I've got a thing minus another thing. Those are two terms. Right? Pi operates very much like a variable until you finally plug in that value, right? As far as the algebra and the simplifying goes. Treat it like an x. Factor it out. Oh, this is pi times 10 squared. 10 squared is, everybody, 10 squared is 100. Minus 3 squared, which is, everybody, 9. Right? And now I only have to put in an actual number for pi once. You see how that's better? That's going to be more accurate, right? Because we don't have a precise, accurate, perfect value for pi, right? It's that infinitely non-terminating, non-repeating decimal of all the numbers ever, right? 3.14159, dot, 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 dot. So the more times you have to enter that approximation into your calculator, or even using the pi button on your calculator, that still only holds so many digits. You're going to lose accuracy. So if we can find a way to, hey, factor it out so we only put it in once, get a slightly more accurate answer. Okay, so 100 minus 9 is, what, 91? So the perfect answer would be 91 pi, right? 91 pi, what are the units here? What? One tick mark is feet. 2 tick marks is inches. Okay? Careful not to confuse that for the 11th power. It is literally the apostrophe key. Okay? So, little note there. Actually, let me make this one purple. There we go. All right, so this is going to be feet squared now, 91 pi feet squared, which is approximately, go ahead and give me 91 times pi button on your calculators. What do you get? Give me, let's go 2 decimal places. $285.74? Okay. Again, 91 pi is the precise answer. It's the exact answer. It's the better answer mathematically. But it's conceptually doesn't immediately ring a bell. You don't look at that and be like, oh, I know how big that is. Whereas if I tell you 285 feet, you'd be like, oh yeah, okay, that sounds like a lot now, right? So I always like include the decimal approximation, just to give yourself a feel for like, okay, where is this number on the number line? How much is that? Any questions on area of a circle? Okay. Then we've got, what, 5 more minutes? 6 more minutes? So your level 1 problems, got a couple parallelograms, a couple trapezoids, 10 area of a shaded region, probably involves some addition or subtraction. Octagon, it is also, it's a ring, okay? I want between 2 shapes. We just did that with the circles, same concept. And a bit of circle practice, and then the best one, the pizza problem, how to get the most pizza for your buck. Really loud. Okay. So I will leave you to get started on that. I'll be around if you have any questions.